Alfonso, senti?
Voi mi sentite? Can you hear me?
Yes.
Okay.
Via.
So you are the chair, so you decide when we are going to start the session.
Okay, maybe there are just the first presenter. I suggest to wait for 5 minutes.
Okay.
Dentro Agent Base c'è questa qua, web.
Okay.
Sì. Ok, perfetto. E questa gliela devo restituire un secondo?
Ci penso io. A chi la devo?
A Damiano. Era nella stanza quando
Sì. Okay. So the first presenter is here. So whenever you want, we can start the session. Thank you.
Hi everyone. Hi Mauro.
Hi. Ciao Mauro.
Ciao.
Come stai? Bene?
Bene.
The first presenter is here. Who is it, the first presenter? Please let me know. Damiano Perri, Giuseppe Capelli e Mauro D'Apuzzo, vedo, che non sono nei nomi dei primi autori.
I am in presence.
Oh, okay. Sorry. Sorry. Okay, then we can start. Okay, good morning, everyone, and welcome to Trust Talk for Smart Cities. Okay? For Smart Cities and this section. This section focuses on innovative approach for smarter and more sustainable urban mobility. Today's presentation offers different yet complementary perspectives ranging from predictive model and real-world application. We'll explore smart parking management using web of technologies, crash severity models for cyclist safety, relationship between bike speed and energy expenditure, pedestrian flow estimation using open source crowd data in Rome, and the last is passenger demand forecasting at the Cagliari-Hermas Airport. This talk highlights how the data-driven solution can support urban transport. I invite you to engage discussion and enjoy the presentation. Well, we can start with the first presentation. I invite Luciano Palesi.
I am Luciano Alessandro Pissaro Palesi from Florence University.
Thank you and welcome. Please.
Thank you. My work is about a web of things-based advanced smart parking management
Sorry
solution.
to interrupt you, Luciano, but we are seeing at home your presenter mode. Could you switch to presentation mode?
Okay. Maybe.
Perhaps you have two screens.
Below on the right, there are.
I don't know why. No. Scusa. Mi chiedono di fare solo una slide, cioè tipo di fare la presentazione solo, però non riesco a. forse setup.
Perché prima non funzionava?
Sì, no, però si vedevano le due slide.
Si vedevano le due slide.
Io le devo faccio vedere.
In modalità presentazione si vedeva lo schermo piccolo.
Maybe display setting. No. Non lo so, perché solitamente a me tipo se faccio
Sì.
da qua si apre tutto.
Esatto.
Forse
Così? Sempre così? Ecco,
è settato così,
impostazione, sì.
No, questo l'ho provato. Setup, maybe presented browser an individual, forse questa. Ok, proviamo. Ok.
Ok.
Okay, perfect. Thank you. The context. Over 53% of the world population lives in urban areas that occupy only 2% of its surface. This concentration, coupled with increased vehicle ownership, has made parking management a critical urban challenge. Usually in the city, drivers spend an average of 15 minutes searching for parking space. And this is a problem for congestion, for fuel consumption, and environment degradation. The main causes are the rapid urban expansion, the growing private vehicle ownership, insufficient urban planning. The solution, the smart city need a smart parking management system that offer a path to enhance efficiency and sustainability of urban transport infrastructure through optimized use of available parking space. In the context of digital twins, digital twins are creating a paradigm shift in urban parking management by providing comprehensive virtual models that enable sophisticated system optimization. The core for digital twin are the real-time monitoring by IoT sensor, for example, in the parking slot, ultrasonic, magnetic, and cameras. And IoT sensors provide immediate occupancy data, processed centrally or at the edge for the reliable updated. Another thing is the predictive analytics. Machine learning models analyze historical and real-time data to identify usage patterns, enabling dynamic pricing strategy and smarter resource allocation that improve revenue while reducing congestion. And the last is the urban planning simulation. Digital replicas allow city to simulate various mobility and parking scenarios, optimize sensor placement, and inform infrastructure development decision for maximum efficiency. By integrating IoT and the Web of Things and machine learning technology, digital twins transform raw sensor data into actionable insight that help city predict, simulated, and optimize parking dynamics. We have two types of requirement for an ideal smart parking system. 5 requirement was a functional requirement. It's important the coverage for entity, for management of the different parking types, for example, street, structure, or private. The dynamic pricing, the mobility as a service integration, user role management, because in smart parking system there is a role for officer, for the end user, for the decisor in the city, etc. And special permit handling, accommodation for resident, disabled user, and other special cases. Other types of requirement are the operational requirement, for example, the smart routing, to move the people in a free parking slot, for example, real-time data, alert and notification for officer and the end user, predictive availability, statistics and key performance indicator for decision driven, and violation management. We based our solution in Snap for City. Snap for City is a platform to perform the whole data flow, from data ingestion to predict and analytics scenario and digital twin. And the platform, this is the architecture. There is a broker. The broker, it's important for data ingestion and data visualization. The IoT sensor send the data into Snap for City by broker, and the data is stored in acknowledged based, and with microservices native in Snap for City, and the dashboard builder native in Snap for City, it's possible create the notification for officer, for example, by microservice based on Node-RED. And visualization is very simple, because people can build the dashboard and see the statistical key performance indicator in a dashboard. After we see an example for the dashboard. The use case for example, for municipal operator, the role for municipal operator is important for live monitoring. There is a dashboard with the map for device status and real-time availability. For example, in this dashboard, it's possible to set to check the parking type, to change the parking type, check parking status, etc. The dashboard for statistical data, for example, with the statistics and make decision from statistic data. And with another management dashboard, it's possible define rate for mixed car, change slot type, and define, for example, the holidays day. Another use case is the end user, the city user. By a mobile app, it's possible create a parking event, start the session in the parking slot, see personal data, and map overview of the situation. In Snap for City, with microservice, it's possible to predict, for example, the slot free near the position, and with a smart routing, it's possible to inform the user to go in the park slot. Another use case is for officer. It's important to detect violation and issue fines using mobile tools. In the dashboard, it's possible to create a fine, search for the fine slot on map, etc. The flow, the interaction diagrams of the solution, usually platform rely on microservice reacting to event streams. This is an example for generic parking workflow. the vehicle park in a position, the sensor send the data in the broker and update status to busy. Update counts on road parking group device, for example. When the vehicle leaves slot, the sensor update status to free, and update count on road parking group device in -1. This is, for example, a solution for end user. We have two types of user, registered user and unregistered user. Anzi, no, registered user and registered user equipped with a sensor. In the first case, the vehicle park in a position, the sensor update status to busy. If the user must renew your parking, have notification for renew the parking, and when the vehicles leaves slot, the system update status to free. Another registered user is, for example, the resident in a city or people with disable, for example, and have Bluetooth device. And when park in a parking slot, the system update status to busy, but there is the sensor Bluetooth to detect the user, and don't need to pay for the parking. Another is for unregistered user, usually with parkimeter, pay the position, pay the parking slot, start the session, and the system when finish the parking, start change the position to busy to free. Another important solution, interaction diagrams for the smart city, is the electric vehicle charging station. Usually the people have or a Bluetooth sensor or a number for charge your car. In this case, the vehicle park in the position, the system update status to busy. When finish the recharge, update the system to be find, and have notification for the people to move the position to the car. We validated the solution in Florence. A simulation system was developed to replicate real-world parking dynamics. We simulated events include random vehicles, user parking spot, and real-time integration with Snap for City API for sensor meter update and control device.
Se ti chiamo.
This is
mi ricordi un attimo, te l'avevo chiesto nel messaggio, qual era la metodologia?
Chiedo scusa, potete spegnere il microfono? Grazie. Prego, può continuare.
There are two example dashboard. For example, in the first dashboard, there are the parking slot. It's possible to see what slot are free, the type of the slot, the trend for availability in a part of the city. And in the second dashboard for decision making, there are the weekly statistics, different for different slots. You can choose and perform your what if analysis in a scenario. With this Snafford City-based smart parking solution, demonstrate significant potential for transforming urban mobility management, provide a scalable, comprehensive framework addressing all essential requirements, effectively ends diverse parking scenario through event-driven architecture, enable data-driven policy making and resource optimization, improve user experience through real-time information and seamless transaction, support broader sustainable urban mobility goals. In the future, with the Snafford City parking solution, our office start for advanced artificial intelligence model, implementing more sophisticated prediction algorithm for higher accuracy in availability forecasting, expanded mobility as a service mass integration, enhanced analytics for make data analytics tool for advanced urban planning application in what if context. Thanks for your attention.
Thank you. Thank you, Luciano. There are some questions, a few minutes to put some questions to the authors. I have a curiosity. I'm curious about if Florence municipality have implemented some dynamic pricing in the city.
In Italy, there aren't cities with the dynamic pricing because the problem usually is the IoT sensor in the parking slot. But it's a requirement for a Cyprus project in Cyprus because we test in a zone with dynamic pricing. Usually, if there are a lot of free slot in the night, for example, the pricing is low. If, for example, usually in the day there are a lot, there aren't free parking, the price was another price.
Thank you. Another curiosity, but how the congestion can affect the system?
Congestion, we have a work for predictive parking slot in Florence, and usually congestion is a feature for the system because the problem is usually in the city, in a city like Florence, for example, the average is 15 minutes to find a parking slot for your car. And if there isn't a planning, it's a problem for congestion because many trips in the street, usually in the peak hours, make congestion in the street.
Thank you, Luciano. Very, very interesting. Now we can move to the second presentation.
There is a question in the office.
Ah, sorry.
In the
Please.
room.
I can see the in the room. I can see in the web. Please, can you introduce yourself?
Because I have been following up this project. I have two questions for you. When I would like to know more because you mentioned KPIs, and KPIs are essential. We need really to understand this framework, what KPIs is using in order to manage in a smart way the parking, the smart parking management. My second question is, what is the predictive accuracy metrics for this framework? Because this is also very important. we do up sensing, but we also need to say at this stage how efficient is, for example, either providing some metrics about the R or the mean standard error. So these are the two questions.
Yes, for municipality, the future key performance indicator are the usage from the people, because there are two types of user. The user use mobile app, and user without mobile app, without account. Is a key performance indicator for municipality is if the local people use the mobile app, use the application. And another need for municipality is, for example, the parking slot. If the average to stay in a parking slot for the people, because for the parking slot there are two problems. There are, for example, people to move in a work, and a good smart city have a solution for these people. Was a solution or public transportation or slot for parking if there aren't public transportation in a zone of the city. And other people are, for example, the tourists. If, for example, in a part of the city where usually the people work, there are a lot of people without registration in the city. This is a problem for municipality because many tourists parking, for example, in this zone because there are parking space. The goal for the Snap for City application is a what-if analysis for municipality. This is a start to data ingestion and create, but for example, key performance indicator, the application developed by events in microservice. Create a key performance indicator is very simple because change the code and read from a device the data, and UAK performance indicator historical with all parking.
And the accuracy metrics, how do you evaluate the performance for this?
Now, the free parking slot, we predict the number of slot parking in a zone, and usually not with on-street road or street parking, but private. When it's possible, count the parking slot in the parking.
Okay, thank you, Luciano. We have a little bit late. Maybe we can continue the discussion in presence with you. Thank you so much.
Thank you.
We have to move the second presentation. And the second presentation, the author is Giuseppe Capelli, Sofia Nardoianni, Mauro D'Apuzzo, and Vittorio Nicolosi, that present interceptor crash and severity protection model to improve cyclist safety. Please, I don't know if Capelli or Vittorio or Mauro, please, can you share the presentation?
Yeah, I'm the presenter, Giuseppe Cappelli.
Thank you, Giuseppe.
Just a moment that share my screen. Okay. Okay. Good morning, everyone. My name is Giuseppe Cappelli, and I'm a research fellow at the Department of Civil and Mechanical Engineering at the University of Cassino in southern Lazio. The title of this presentation, but also the title of the presented paper, is Interpretable Crash Severity Prediction Model to Improve Cyclist Safety. The reason why to focus on cyclist safety is that in the last year, all over the world and also by the European Commission, there is the need to improve road safety and also reduce vulnerable users crash. For instance, the Vision Zero want to reduce to zero in the next 25 years the number of road crashes. According to some statistic, in 2021 there was 1.90 million of road deaths, and a vast majority of these road deaths regards pedestrian and two-wheeler users, such as cyclists and micromobility users. In addition to that, the country in the north hemisphere are experiencing an increase of vulnerable users demand. So it is expected that in the next years, if that number of cyclists or pedestrians will increase also the risk to be involved in such type of crash. There are some theories such as the safety numbers that goes in contrast to what now I've said, but there is no strong evidence that this phenomena is linked to an increased safety for vulnerable road users. Because this theory remains already yet debated, it is essential to try to improve road safety to assess the risk related to a crash. From a transportation point of view, we can evaluate risk as the multiplication of exposure, hazard, and vulnerability. For exposure, we mean that exposure is the number of road users that are exposed to risk, and so the probability of having a road users exposed to risk. The hazard, that is the conditional probability of having a crash. And lastly, vulnerability is the probability of having a fatal or a non-fatal outcome, and this vulnerability is something related to the severity of the crash. In this paper, so we focus on the last terms of that equation to try to predict the severity of a road accident. This model is important that if a road crash happen, with this model we are able to predict the outcome of the crash itself. So if this crash leads to a death or to an injury outcome, to try to answer this question, we use a simple logistic regression. The reason why to use this logistic regression is that first, it is a simple model, and secondly, is an interpretable model. Nowadays, we see everywhere machine learning models that are implemented in everyday life, but the major drawback of this model is that they works as a black box, so there is a lack on the interpretability side. With logistic regression, we try to overcome this problem related to interpretability. Going to the case study, we focus on in particular on the city of Rome. And we analyzed the crashes in the city of Rome, cyclist crashes between 2060 and 2080. In this 3-year time period, we registered 885 cyclist crashes. So the dataset that we used to make this analysis was a dataset provided from the agency Roma Mobilità in Italian. First of all, we conducted some descriptive statistical analysis to have an overview of the problem, and we can see that the vast majority of cyclist crashes lead to injuries, and only few of them lead to a death outcome. In addition to that, we can see that a great percentage of cyclist crashes happen during spring and autumn, according to the analysis that we have performed. There is also an hourly and a daily trend, and for instance, we see that in these two graphs that a great percentage of cyclist crashes happen during off-peak period time, so between 8 and 10 a.m. and to 6 to 8 p.m. A great number also of road cyclist crashes happen during the weekday. During the weekdays, so to Monday to Friday, when during Saturday or Sunday there is a decrease in cyclist crashes. We make also some statistical analysis, take into account the average daily traffic and the vehicle speed, as it's possible to see in these two figures. The number of deaths decrease with an increased number of the average daily traffic, while the number of deaths increase with an increase in vehicle speed. After this brief statistical analysis, we try to create this general crash model by using the datasets provided by Roma Mobilità and the logistic regression. Here in this slide, we see a summary of the variable that were used in this model, and it's possible also to see the prediction performances of the model. It's worth noting the McFadden, that is called also pseudo R-square, that give an information on how accurate is the model. Usually, acceptable range of this value fall under the range 0.2 to 0.4. So with this 0.13, we are below to this sort of threshold acceptable range. To try to improve this model, we focus on specific crash scenario. So first of all, we try to, in order to improve the performances, we focused on what happened on intersection. So in this case, we apply this model by highlighting all what happened on intersection. As it's possible to see by the estimate of the coefficients of the coefficient of the variable used, and also the p-value, it's possible to see that during weekday and during evening and night hour, the probability of having a fatal death increase. The probability of having a fatal death increase also when this speed exceed the value of 50 kilometer per hour. Another crash model that we have created to understand the role of the single variable to the outcome is this crash prediction model for single lane carriageway. According to the result that we have obtained, if we move to an extra urban location during a weekday, the probability of having a fatal crash increase, but the probability of having a fatal outcome increase also when the average daily traffic increase beyond 2,000 vehicles, and also when the speed exceeds the value of 50 kilometer per hour. As last step of this analysis, we make some comparison. First of all, we assess the McFadden pseudo square in order to highlight model performances, and we can see that for intersection single lane carriageway, we are beyond the optimal range that is usually considered good in the current literature. We made also some sensitivity analysis by removing the variable speed and the variable related to the average daily traffic, and we saw that if we remove this variable, the prediction performances of the model decrease as well. In addition to that, we also try to make some comparison with models observed the model create according to the literature, and we saw that the results that we obtain are in line with this model that we found in literature. Going to the conclusion, and I want to be very brief, it is important when we want to predict the outcome of the accident. It is important to take into account variables such as daily traffic or flow, for instance, and speed. And if this value exceeds some threshold, the probability of having a fatal crash increase as well. As future development, we want to extend this time period analysis to more than 3 years, and also extend this type of analysis to other Italian contexts and European contexts, and also to study the vulnerability of other vulnerable users. Thank you for attention.
Thank you, Giuseppe. There are any questions from online participants, or I can able to check if there are some questions in presence. Alfonso, can you help me in this? In that case,
there are no questions from the room.
No, thank you. I have just a curiosity. I'm very surprised because the visibility is not a key factor. It is one of the infrastructural elements that more affect the safety. What kind of comments about that?
Yeah, the problem is strictly related to how ISTAT, or in this case, Roma Mobility, collects such type of features. So is something different to the visibility that the transportation engineer is used. So, for instance, the variable related to visibility is good visibility, not good visibility, and
that's all.
and so on.
Okay, understand. I'm agreeing with you. Not all elements are verified during the check-in by the officer. Okay, thank you. The next presentation is also Giuseppe Capelli, Sofia Nardoianni, Mauro D'Apuzzo, e Vittorio Nicolosi. A macroscopic physical-based relationship between bike speed and energy expenditure during commuting tips. The presenter is Mauro D'Apuzzo, I suppose.
Yes, correct.
Thank you, Mauro.
Correct. And let me share my screen. Okay. Could you hear me and could you see my presentation?
Perfect. Go ahead.
Okay.
Perfect.
Thank you, everyone. I'm Mauro D'Apuzzo. I'm full professor of Highway Design Traffic Engineering at the Department of Civil and Mechanical Engineering at the University of Cassino in Southern Lazio. And I would like to present a paper entitled "The Microscopic and Physically Based Relationship Between Bike Speed and Energy Expenditure During Commuting Trips." I would like to thank my co-author, Giuseppe Cappelli, Sofia Nardoianni, Vittorio Nicolosi, Heather Katz from Wuppertal University in Germany, and Maria Teresa Iannattone. This is a work that, as a matter of fact, Giuseppe Cappelli carried out during his stay in Wuppertal University, hosted by Professor Katz. And I would like to share with all of you first results of this work dealing with energy expenditure, that is a parameter that is usually a common parameter used in, I would say, sports science, because we need to remember that when we talk about cycling transport mode, and so obviously we are talking about micromobility, and we are talking about sustainable mobility in urban areas. So the main focus of this work is obviously framed in a higher framework dealing with sustainable mobility in urban area. Obviously, we need to consider that when you use a bicycle, obviously you will have to spend some energy, since even the electric bike are operating basing on some muscular energy, even if it's not the overall energy and power that is used for the motion of the bicycle. So we start from the assumption that when a person will use a bicycle for commuting purpose, it involves a physical activity powered by hydrolysis of ATP, and energy expenditure is a key parameter to capture this phenomenon. And usually it can be measured by power applied to bike pedals, or using strain gauge, and by other means of monitoring this parameter. But the problem is that such monitoring methodology are quite difficult to be applied on a large scale due to high cost and limited attention. And therefore, we came up with the idea that we can try to capture this parameter that we are confident can affect mainly the bike choice in the transport demand by using some, I would say, surrogate parameters that are related to energy expenditure. And one of the most significant surrogate parameter is terrain slope. So we are pretty confident that we can use terrain data in order to have some significant information on energy expenditure related to the use of bike in urban area. As a matter of fact, this work is a part of a larger research study that we started some years ago on Italian cities. So we want to study the influence of terrain data on energy expenditure and on therefore on bike mode split in Italian context. And we investigate of a sample of Italian cities with the ranging with the variable size in terms of inhabitants from 0 to 10,000, 10,000 to 50,000, and from 50,000 to 100,000, on which we collect several data that were related to terrain slope, but also to cycle line supply, and also some land use data in order to develop some regression model that can provide us information on bike split. And we came up with formally with three different regression model according to the specific size range of an Italian city, because we effectively check for the importance of the size of the number of inhabitants in the city in the bike split model. And we were obviously curious to check whether similar model can be derived from another context, another national context, and we came up with the idea that perhaps we can study same relationship applied to the German context. So first time we collect data on terrain on a sample of German city. And as you can see from the flow chart in the left side of the slide, we follow a procedure starting from collection terrain data, then evaluating the power required during cycling using the tractive force equation that is very well known by all highway engineers. And from this tractive force equation, we came up with the obviously with the power. And when we have the power, we can also evaluate the oxygen consumption relating to a specific trip that is demanding a specific power. And finally, we can, from the oxygen consumption, we can evaluate the energy expenditure during cycling activity. That is, as I told you, the physically based parameter that we already check in the Italian city and that we want to test against a sample of German city. So just rearranging all this relationship, we came up with a relationship expressing the energy expenditure as a as a function of bicycle speed and also on slope. The advantage of use such derived relationship is also related to the possibility to take into account, obviously, the use of electric bike against the what we call the conventional or muscular bike that obviously were traditionally used in cycling. So we can take into account the use of e-bike just by assuming what we call an assistance ratio, that is a dimensionless parameters that can allow us to model also the use of this e-bike that, as you know, are spreading throughout our cities and in general in the European Union recently. So, as previously said, we test this model against a sample of 61 German cities. As a matter of fact, we were somehow forced to select a sample that was characterized by a number of inhabitants higher than 100,000 inhabitants for each city, and we collect some data on population area, land use, and various econometric data, other than obviously bike mode split and other transportation split percentage. And applying by making use of the previous relationship and apply this to the sample of German cities, we came up with a general relationship, is a linear relationship relating the average cycling speed with the energy expenditure that could be useful when we want to, for example, try to experimentally validate this relationship by using some monitoring data on some testing cyclist. So I'm just talking about, installing some monitoring sensor in order to gain the energy expenditure in order that can be used to validate this relationship. And obviously we can also came up with another linear relationship relating the energy expenditure and the slope parameter characterizing the single trip performed by bike. If you use a conventional, we call it C-bike, or an electric bike. We obviously perform several statistical tests in order to verify the statistical significance of various explanatory variables on which we collected data on this sample of German cities, and we came up with a final relationship relating the bike mode split to the energy expenditure that is reported here with all the relevant statistics. We effectively collect data on cycling lane supply, but according to our test, we came up with the results that for this sample of German city, cycle lane supply is not significant. Well, the interpretation for these results that obviously is different from that we gained for Italian city is perhaps related to the fact that cycling mobility in German is much more, I would say, advanced and evolved compared with the Italian one. I mean, there is a cultural, I would say, familiarity with cycling mobility in German cities. So obviously the bike split value are much more higher than those relating the Italian one, because we are, I would say, we are in Italy, we are still in a sort of primitive stage of cycling mobility. If we just compare our figures and our numbers with the German, or for example with the Netherlands, so that's why the cycling lane supply does not play a significant role in this regression model. So just going straight to the conclusion, this research centers of energy expenditure as a key factor influenced by commuting. It aims to find reliable relationship between energy expenditure, cycling speed, and demand using microscopic physics-based approach. Studies or uses open source geographic and terrain data to simulate commutes and calculate energy needed. Energy expenditure is tested as predictor cycling demand. The study compares electric and conventional bikes, showing how energy use, speed, and slope interact, and propose models where energy is the only variable. This obviously may have some impact on urban planning. Results support the idea that energy force should be factored into cycling infrastructure design to enhance accessibility and promote commuting by bike, especially in hilly areas. Future developments obviously is to improve the model. Actually, the current model explains up to the 40% of variance, and more field data on commuter cyclists are needed. The results support the idea that energy effort should be factored into cycling infrastructure design to enhance accessibility by bike mobility. Thank you very much. I'm taking any question.
Thank you so much, Mauro. There are any questions from the audience in presence or from online? I have a curiosity about just a practical application for urban planning, Mauro, or designing cycling infrastructure in the cities. Of course, in Italy, we have a different morphology of Germany or Netherlands, I used to mention. I have an e-bike. You know, because in my city,
as a matter of fact, also my wife uses an e-bike to go to work. He's a teacher in a school, and he use a e-bike. E-bike are really spreading in urban city, because obviously, as you can see, they can also imply lower insurance cost and absent formally insurance cost that will, as you know, in Italy are quite high for all the other transport modes. Sorry, I interrupt you. Your question.
No, the question is what about the implication for the designing cyclist infrastructures?
Yes, the implication is that obviously is may appear some sort of trivial results, but we are still convinced that some physics-based relationship will affect the bike mode. And the implication in cycling lane design is that the designer should, for example, try to identify the less hilly cycling paths if they want to promote the biking in urban area. And another implication of these results is that usually the bike demand is studied by means of discrete mode choice models by transport engineer, okay? And the fact is that usually these discrete mode choice model are usually developed on a site, on a specific site, collecting data on by means of survey. And the results of this study show us that we need to take into account also the terrain in the variable in order to extend these discrete choice models to all the other cities and sites in Italy or in Europe. I don't know if I correctly answered to your...
Yeah. There are a lot of questions about payment quality and so on. Thank you, Mauro. Then we can move to the next presentation, the next paper presented by Sofia Nardoianni, Giuseppe Cappelli, Mauro D'Apuzzo, Vittorio Nicolosi, and Mariano Pernetti. Estimation of pedestrian flow with open source crowding data, an integrated model in Nomentano Tirbutina district room. I suppose the presenter is Sofia Nardoianni?
Yeah, sure.
Okay. Thank you so much.
Thank you. Good morning, everyone. I'm Sofia Nardoianni. I will present the work entitled The Estimation of Pedestrian Flow with Open Source Crowding Data, an integrated model in Nomentano Tiburtina District, Rome. Before starting, I want to thank my co-authors, Giuseppe Cappelli, Mauro D'Apuzzo, Vittorio Nicolosi, and Mariano Pernetti. Among the sustainable modes of transport, the one that is becoming increasingly popular is on the foot mode, defined as a soft mobility. Certainly, an increase in walking helps to reduce greenhouse gas emission that would be recorded if, on the contrary, a motorized vehicle was to be made. In this slide, present the distribution of road traffic deeds by type of road user, with a particular focus on pedestrian, both globally and in Italian context. Globally, we see that in many low and middle-income countries, pedestrians account for a high percentage of road traffic deeds, in some cases over 50%. This highlights the lack of the safe infrastructure and unbalanced mobility systems. Looking closer at Europe, we can observe that Italy shows an intermediate share of pedestrian fatalities, around 20-22%, while in countries like Romania, the percentage is significantly higher. This figure underlines the importance of continuing to invest in the safety vulnerable road users, especially pedestrians, cyclists, and macromobility users. In this regard, it is necessary to investigate pedestrian flows that affect urban areas to guarantee safe pedestrian paths and avoid not allowed crossing outside approximately built crossings by pedestrians, which lead to an increase in accident risk. To evaluate the pedestrian crowding present in the study area, take into account completely the behavior of pedestrians, an integrated configuration model was developed that see the combination of digital and physical approaches. As far as the development of the digital model is concerned, the Quantum G software was used. In particular, first it is planned to define the pedestrian network of the case study, then through the syntax application, explore the influence of the study area on configurational parameters, focusing on factors related to both demand drivers and land use, which can have a significant impact on the pedestrian density. Among the factors considered are the population density, the estimate of which was possible thanks to data from the Italian National Institute of Statistics, and the presence of commercial activities along the pedestrian network. The data which were retrieved from the Google platform, in particular from the Google Street View application. Alongside the digital model, a physical support model has been developed that aims to make the digital model previously developed as real and accurate as possible through a calibration of data. Therefore, for the development of the physical model, it is necessary to carry out a collection of experimental data on the pedestrian crowding of the area under consideration. The most common method of doing this is that of the mobile observer, which consists of an observer or a team of observers who physically moves around the study area, usually walking along a predefined path, recording the number of pedestrians present in the areas and their relative position. To obtain geolocated data, observatories can also be equipped with GPS devices. However, this methodology can be applied to small and medium-sized areas, but is more difficult to implement in larger areas, such as the one in the case study. To endorse this, virtual data collection methodology was developed through the use of Google Maps Street View mode, which could be appropriately calibrated so as to have data similar and precise as possible to that which could have been collected with the mobile observer method. However, the collection of data from Google Street View has gaps and therefore can be less reliable than the other methodology mentioned above. To overcome this, the present research studies an appropriate calibration between data collected virtually and data collected through conventional methodologies. From previous study in which the configurational mode was applied to a small medium-sized reality, there were data characterizing pedestrian flow collected through a mobile observer. For this area of interest, therefore, the same data were collected by in a virtual mode through the use of Google Street View. Then it proceeds to identify a literature partner that could have a trend similar to that of the case study to be able to scale the data collected virtually for all hours of the day. Once this was done, it was possible to find a discriminating factor between virtual data and data collected by mobile observer.
Sofia, sorry to interrupt you, but I don't know if you are looking at the next slide because we are still stuck in the slide number 4. So I don't. Okay.
Okay.
Now it's work.
Yeah. Yes.
Okay. Thank you.
Perfect.
Thank you. Okay. The case study falls on an area of municipality of Rome called Nomentano Tiburtina. Located in the northwest quadrant of Rome, the Nomentano Tiburtina area sees the influence of numerous significant attractions, such as the Nomentano Tiburtina station, one of the main transport hubs of the capital. To this is added the proximity to La Sapienza University and Umberto I Polyclinic, which attract students, workers, and visitors daily, creating a mix of constantly moving pedestrian flow. The main arterials such as Via Nomentano and Via Tiburtina are also significant for the impact of pedestrian crowding, as they act as commercial streets. The medium-sized area that was used to validate the data collection methodology through the Google Maps Street View application falls within the municipality of Cassino, located about 140 kilometers away from Rome. The significant activities fall around Corso della Repubblica, the main artery that crosses the city, where there are shops and various commercial activity. The university also generates a constant flow of students, faculty and staff, which adds to the daily movements related to commercial activities and public services. As far as the digital model is concerned, it has been developed using special data analysis software such as QGIS, and in particular the space syntax tool that allow to carry out a configurational analysis of the pedestrian network and obtain a quantity called integration, which allowed to express pedestrian crowding. The study on pedestrian crowding in Cassino was developed from a previous study, while as regard the Nomentano Tiburtina area, following an analysis previously carried out where pedestrian crowding was expressed only in terms of integration, and influence parameters such as the presence of shop was investigated. First of all, it was necessary to identify the shop on each arch characterizing the pedestrian network of the Nomentano Tiburtina area. To do this, the Street View application Google Map was used. Once the shops that insist on the pedestrian network had been identified, it was possible to define an ad hoc methodology to be able to evaluate the value of integration that takes into account the influence of shops. A correction coefficient called K-shop was first evaluated, which sees the relationship between the average length of the shops and the length of the district affected by them. Once the K-shop coefficient has been defined, it is possible to evaluate the integration that takes into account the influence of the shop on the pedestrian network. The physical model is based on the evaluation of the number of pedestrians present on the networks. In this case, as previously defined, a new methodology has been developed to carry out pedestrian counting in a virtual way on large areas such as Nomentano Tiburtina. This methodology was validated on medium-sized realities such as that of Cassino and then applied to that of the case study. First of all, data were collected on the pedestrian count on the Cassino pedestrian network with the mobile observer method. The processed data used for this research refer to average data of typical working days, referring to the following time slot: a morning slot, an afternoon slot, and an evening slot. The same work was conducted virtually thanks to the use of a Street View application of Google Maps, which, however, returns the count of pedestrians in a single instant of a typical day when the Street View car passed through the case study location. In light of this, on Google Maps, a date was set on a typical weekday and data collection was carried out. However, this is not enough. It is necessary to know the time slot during which the Google Street View vehicle made the passage and therefore which refers to the data collection carried out. Thanks to the use of software that allow from the study of the shows present in an image of interest to define the time to which the image refers, it was possible to estimate the time of passage of the Google Street View car and therefore estimate the time on the virtual data collection of pedestrians, which turned out to be around noon. Therefore, the need arises to obtain data that also refer to the other hours of the day in order to be able to compare them with those collected with the mobile observer method. First of all, the correlation between the data collected in a virtual way and those collected through the mobile observer method in the various time slot described above was studied to understand in which time slot the best correlation is recorded and to be able to confirm that the data collected virtually refers to a late morning time, in particular at noon. The best correlation is obtained for the afternoon time slot, confirming what was previously defined. To obtain data that refers to the entire pedestrian flow pattern, a literature pattern that reflects the trend of the case study pattern was considered. In both patterns, there is a peak in the lunch slot around the 1 p.m. With periods of softness in the night and the later evening slots. The methodology adopted sees the identification of the value of the pedestrian flow in the literature pattern relating to the noon, considered as a reference base. Therefore, for each hour of the day, an hourly coefficient was evaluated by dividing the value of the pedestrian flow corresponding to noon by the value of the pedestrian flow corresponding to the other hours of the day. Once this was done, in order to evaluate the values of the pedestrian flow for each hour of the day, referring to the case study, a proportional approach was adopted. More specifically, for each hour, the value of the pedestrian flow observed with the use of Google Street View at noon relating to the case study was divided by the corresponding coefficient calculated from the literature data. This has made it possible to obtain an hourly distribution of a typical weekday of the pedestrian flow following within the area of the case study, consistent with the pattern reporting the reference literature. This evaluation was carried out for each arch of pedestrian network of the case study, for which there are counts of pedestrian flow. The pedestrian flow pattern, therefore relating to the case study, show the trend below. In order to make comparable in terms of time slot, the counts of a pedestrian flow obtained with the method of the mobile observer and the related ones obtained thanks to the virtual collection with Google Street View have been recognized. Comparing the counts, the results obtained is shown. It is possible to define the relationship between the data collected with the mobile observer method and those collected through the use of Google Street View, reaching an agreement that sees the definition of Pearson equal to 0.73. Thanks to this relationship, it was possible to collect data on pedestrian flow in the Noventano Tiburtina area and appropriately scale this data using the relation defined. With a coefficient as 0.78. In order to have a model as close as possible to reality, calibration was carried out between the digital model created with the QGIS application space syntax and the physical model from which it was possible to obtain data relating to the pedestrian flow. However, as far as the digital model is concerned, several cases are analyzed to understand which digital model best fits the physical model. The analysis evaluates the relationship between the estimated pedestrian flow corrected with the different weighting factors and pedestrian flow observed through Google Street View. In particular, two different corrections of the digital model were considered, one based on a weight of proximity, which takes into account the distance concerning certain areas of interest, and another that integrates a factor related to the presence of commercial activities along the pedestrian network. The survey was conducted both in the case where the study area corresponding on Noventano Tiburtino district was considered in isolation, excluding the influence of a neighboring municipality, and the case where this influence was maintained. The comparison between the pedestrian flow deriving from the corrected digital model and those estimated through Google Street View made it possible to evaluate the impact of each weighting factor on the accuracy of the forecast, and to understand how the territorial configuration affects the distribution of pedestrian traffic. By this, the Pearsons of the various proposed cases were evaluated, and the best correlation between the digital model and the physical model can be obtained by considering only the area of Noventano Tiburtina case study without the influence of the neighboring municipality, and considering the digital model that takes into account the presence of shop along the pedestrian network with a Pearson equal to 0.88. From the processing of the data obtained, it was possible to evaluate the propensity to cross pedestrian in this way. In conclusion, it is possible to confirm the validity of the proposed integrated approach, highlighting how the combination of digital and physical models represent an effective tool to analyze pedestrian flow and support urban planning. From the analysis carried out on the area of interest, such as the Noventano Tiburtina district of the city of Rome, it was possible to identify the predominant factor that influences pedestrian behavior, such as the presence of shop along the pedestrian network. In addition, a new virtual data collection methodology has been developed, suitable, calibrated, which allow data on pedestrian flow of large areas of interest to be collected quickly and easily. In light of the results, therefore, the present research aims to make a significant contribution to the understanding of the pedestrian dynamics and offers a starting point for future studies aimed at an optimized soft mobility in complex urban contexts. The calibration of the digital model obtained from the correlation with real data, which results in a Pearson equal to 0.88, demonstrates the effectiveness of the analysis and how the model developed is as close as possible to reality. In the future, the goal is to improve the investigate more about the virtual data collection method in order to optimize it and make it computationally as simple, but at the same time as accurate as possible. In order to have not only data relating to a specific time of the day, such as the offered by Street View, but also to have a complete pedestrian range pattern, we propose to exploit existing technology for complementary applications, such as cameras installed for monitoring climatic events. Thank you for your attention.
Thank you, Sophia. Thank you so much. There are any questions from the audience in presence and online? I have just a comment, Sophia. Of course, your work is useful in the opposite way. If I am owner of the shop, of the restaurant, I can use your model to the best localization of my shop. True. No, this is very useful for to allocate the different kind of shop. Of course.
Yeah, of
Okay.
course.
Thank you so much. Thank you. We can move the last presentation. The last presentation, the author is Nicoletta Rasso, myself, Riccardo Zedda, Kevin Panetta, Francesca Maltinti. A multivariable econometric model for forecasting passenger demand at Cagliari Airport. Okay, the presenter is Riccardo Zedda. Please, Riccardo, share your presentation.
Everyone, and today I talk about the study of an econometric model for forecasting air transport demand, the case of Cagliari.
Please, okay.
Okay. Between 2014 and 2019, Italy...
Move to the, sorry, Riccardo, move to the presentation mode.
That's okay.
The button. No, it's the same. Maybe you have to. Okay, go ahead. No, nothing moving. Okay. Don't worry. Okay.
I'll try.
Like to say. Go ahead. No worry.
The passenger traffic in Italy record significant growth trends. In fact, for example, in the island, we have a plus 5.6%, and the south 8.9%, and the north 5.9%. Globally, air traffic is showing a rapid post-pandemic recovery, and in 2022, 6.6 billion passengers were transported, with a growth of 43% compared to 2021 and 72.5% compared to 2019. In 2024, for the first time, we are surpassing the level of 2019. The increase in air traffic triggers a real chain of economic effect. In fact, we have a growth in tourism, GDP increase, and a rise in employment. Such sustained growth brings challenge and requires target intervention. We have pressure on airport capacity, the need to balance supply and demand, and trade-off between different infrastructure.
Your presentation is stuck on the first page. Okay. Sorry to interrupt.
It's okay.
Yeah, now we can see the page 3. Thank you very much.
So we can have with solution the adoption of larger aircraft, efficient master plan, and flexible design. This challenge can only be addressed through an organic planning of air transport articulated on 3 levels: airport system planning, master plan development, and executive design. This study focuses on development of master plan at the local level, applied to specific context of Cagliari-Elmas Airport. Forecasting the evolution of air transport demand is an essential pillar for effective air mobility planning. There is a close correlation between demand and supply. Understanding demand dynamics is the key to properly sizing infrastructure, optimizing available resources, and planning target investment. The master plan is structured in the following phases: an overall vision, targets and goal, environment analysis, current state of existing infrastructure, and forecast of air transport demand. In particular, The objective of this study is precisely located the fourth phase of the master plan, the forecast of air transport demand. This activity is essential to size the Cagliari-Elmas Airport according to traffic forecast, ensuring consistency between overcapacity and expected demand. There are different approaches to estimate air transport demand, classified by their underlying statistical methodology. We have behavioral models based on individual travel decision, the simple time series which extrapolate the historical trend without explaining their causes. Causal modeling divided into regressive methods, which search for functional relationship between demand and the explanatory variables. Moving average method, which synthesize the trend of past residuals, and Box-Jenkins method, the ARIMA models, which combine autoregression and moving average applied to different series. This study integrates Box-Jenkins model with a regressive method, creating a multivariable econometric model that combines the strengths of both methodological families. The multivariable regression model is the econometric model that allows to estimate the number of passengers as a function of the explanatory socioeconomic variable predicted with ARIMA models. The basic structure of the model is expressed by the following equation, where yt is the dependent variable representing passenger demand in the year t. The x are the explanatory variables, for example, the socioeconomic factors influencing demand. The beta coefficients are to be estimated, measuring the strength of relationship between each x and y for every year. The epsilon is the error term, capturing variation not explained by the model. The projection of the x are obtained using a Box-Jenkins ARIMA with multiple regression, quantify the combined effect of explanatory variables on air traffic demand. The ARIMA model for socioeconomic variables are derived from integrated ARMA in PQ models D times to achieve sectionality. The ARIMA model is composed of three elements. The autoregressive part that includes the contribution of the last p-values of the series, the degree of differencing applied to make the series stationary and remove trends on seasonality, the moving average part that includes the effect of the last Q errors, and the basic equation that we can see in the slide have the objective to analyze a non-stationary series and predict future values using regular patterns from historical data. The construction of the econometric model consists of 6 steps. The analysis of independent variables, the research of functional links between dependent and dependent variables, investigating the functional relationship, the econometric model construction, the generation of the future socioeconomic scenario using ARIMA models, the calibration of the econometric model using real data, the final elaboration of traffic forecast. The choice of variable favors those with proven relevance, avoiding redundancies that could reduce estimation accuracy. To define the influence of area of Cagliari-Elmas Airport, the isochrone method was used, with the calculation of road travel time required to reach the airport, and the objective to identify areas already served within the current catchment and detect potentially integrable new areas. The territorial areas considered were the metropolitan city of Cagliari, the South Sardinia, and Oristano. Then, to evaluate the trend of main traffic indicators, the variation index number is used, where VI is the value of the indicator in the current year, and VB is the value of the indicator in the base year. The index summarizes in percentile term the evolution of variables such as passenger, movement, and capacity. The analyze indicator, all expressed using the number index, include also regional value added, labor force activity rate, resident population, motorization rate, tourist arrivals, and the formula for index repeat here as well. After generating all possible regression between passenger and socioeconomic variables, each equation was accompanied by the R-square coefficient, which measure the model's fit to empirical data. The most represented variables were then aggregated into a single multiple regression, obtaining the final form of the multivariable econometric model. After the multicollinearity check, we had 14 models were created with different variable combination, and the best model were compared to identify the most robust. ARIMA models for each socioeconomic variable were implemented in Python using historical series up to 2023 as input. The code explored various P, D, and Q configuration, choosing for each series the parameter combination that minimize the forecast error up the 2040 horizon. Among the 5 series examined, we selected the four best series, and 2 show particular divergent behaviors and had a decisive influence on the econometric model selection. In fact, the number index of value added and the tourist arrivals. Also, the population index, the motorization rate index had a difference in about a negative value of 17%, and the motorization rate index about a positive of 29.85%. And the other 2 main variables considered were the motorization, also the motorization rate and population, completing the model explanatory set. The multiple regression takes on the following matrix form, where Y is the vector of yearly passenger forecast. The X are the matrix of forecasted series via ARIMA, and the beta vector of previously estimated coefficient. Epsilon vector of residual errors. The only unknown to be determined is Y, solved through a multiple regression. Among the 14 initial models, those with the best statistical indicator were selected and calibrated on year 2024 by comparing the values predicted by the regression with the actual observed value. The model with the smallest percentage deviation was identified. The select model is described by the equation in the slide. The characteristics of the model are R square about 0.91 and adjusted R square about 0.89. Also the parsimony. In fact, there are only 2 variables, the tourist arrivals and the motorization rate. Also the explanatory power with high fit to historical data. A lower average percentage deviation, about 3.30% compared to other models, and the consistency with ENAC forecasted to 2035. In fact, with the model, we have a forecast of a growth versus 2019 about 48%. With the ENAC forecast range based on year 2019, we have a growth minimum of 41.2% and a growth maximum about 62.5%. By calculating a confidence interval for the 2 explanatory coefficients, 3 demand scenarios for 2035 were generated, comparing model estimate with ENAC data reveals. The driving variables remain tourist arrivals and motorization rate. And we have a difference in pessimistic scenario about 0.15% and an optimistic about 3.86%. In conclusion, the model balances simplicity and predictive power. The ARIMA was integrated with multiple linear regression, and validation were conducted throughout multicollinearity and deviation analysis. Forecast align with the National Airport Plan of ENAC, and the contribution of the study is provide an advanced analytical tools for airport planning and flexibility and adaptability to the specific context of Cagliari-Elmas. The future implications are forecasting methodologies adaptable to changing social scenarios and methodological basis for further research, such as with neural network or machine learning. Thank you for your attention.
Thank you, Riccardo. We are perfect in time. Thank you all for the respect the scheduled time. Asking everyone. Just one comment, Riccardo. A question. The period cover a COVID pandemic period. How do you treat the data in order to filter to management this problem?
Yes, the data about the pandemic period were studied, and they were a big outlier. And we try to model with the classical multiple regression, and we have we saw the differences between the use and the non-use of this data. And so we decided to cut the 2020 and the 2021, and we linked the 2019 to 2022, because there is a direct correlation between the 19 and the 21. So we decided to cut the data of the pandemic period.
Thank you. There are any other questions for Riccardo? Alfonso? None from the room. Finished. Oh, okay, thank you. Thank you, Alfonso. Thank you, everyone. This is a nice section. Be grateful to my colleague Mauro and Alfonso and so on. Thank you, and see you soon.
Thank you, everyone. Thank you, Mauro, for your brilliant coordination. See you.
Thank you. Bye-bye. Bye-bye, everyone.
Bye. Bye.